Me da mucho gusto presentar a Felipe Rodríguez. ¿Se lo digo en inglés o en español? Español. Para los que no están enterados. Luis es investigador emérito de la UNAM. Él obtuvo su licenciatura en la Facultad de Ciencias de la UNAM y su doctorado en la Universidad de Harvard. Y él trajo a México la técnica de la radioastronomía. Él fue el pionero que estableció esa técnica en México y la ha utilizado en muchos campos, especialmente en la formación de estrellas y planetas. Y tiene alrededor de 500 trabajos que han recibido más de 27,000 citas. Y entre otras muchas distinciones, recibió el Premio Nacional de Ciencias y el Premio Bruno Rossi de la Sociedad Astronómica Americana. Desde el año 2000, Luis es miembro del Colegio Nacional y en el 2008 ingresó a la Academia de Ciencias de Estados Unidos. En 2021 recibió la cátedra Jansky que otorga el National Radio Astronomy Observatory, que es la distinción más alta que se tiene a nivel mundial para los radioastrónomos. Y por supuesto, para los jóvenes, Luis es el fundador del instituto finalmente, y si no fuera por él no estaríamos platicando. Así que,
thank you very much. I think I will give the talk in English because I have the view graphs in Spanish. So this afternoon I'll be talking to you about the detection and radio waves of what appears to be a binary system of planets. And these are planets not associated to a star. These are the so-called free-floating planets, or rogue planets as they are called in English. And these are planets that are not associated with a star. And this in itself is a problem, because the idea we had in the star formation was that a clone exceeding the gene's mass will contract and form one or two stars. And around those stars, the planets will form in a disk as a secondary product of a star formation. But apparently these free-floating planets somehow managed to either form as a star, which we don't understand, or were ejected from a planetary system somewhere in the region. So, and please stop me if you have a question. This is work that I have been doing with Luis Zapata, with Laurent, and with Gisela Ortiz, who is now has a position at the INAORE. Well, as you know, bodies that have stellar or planetary masses are divided in three broad categories. Anything that is more massive than, let's say, 80 times the mass of Jupiter are supposed to be able to sustain hydrogen fusion and are called stars. In between stars and planets, there are these bodies called brown dwarfs, which have masses between 13 and 80 times the mass of Jupiter. And finally, things that are below 13 masses of Jupiter are considered planets or exoplanets, of which we have a lot. So remember this number, 13 Jupiter masses are the threshold between planets and brown dwarfs. Well, brown dwarfs in themselves have different categories. With more and more observation, people realize that they have a sequence also, which is cataloged in these letters M, L, T, Y, and in order of decreasing temperature. So actually, the less massive the brown dwarfs are really cold. They have only several hundred kelvins. And here are examples of those brown dwarfs. Well, now over the years, of course, we radio astronomers, whatever it can be seen in other wavelengths, we try to see if we can detect in the radio and understand what is the mechanism. And over the years, with respect to stars, there have been radio detections of stars, basically of all sorts. You see, this is an HR diagram, and the dots are detections of stars in the radio. And one first thing that you can see as well is that there are detections all across the HR diagram, and also that the more massive the star, that is in this region, the more radioluminous there are. The size of these circles is related to the luminosity in the radio. So as we go to less and less massive stars, we detect them in the radio, but they are less and less luminous in the radio. So you may be asking, what are we detecting in the radio? Well, here's this equation that is very important, and it just basically tells that the flux density of an object in micro-Janskis. Now, sensitivity is very good, and we are talking of micro-Janskis. In the 1960s, people would talk about Janskis, then in the 80s and 90s, milli-Janskis, but now the systems are very sensitive, and we're talking about micro-Janskis. But if we put in here the parameters of a star like the sun, with a surface temperature of 50 K, solar radius, and the distance of Orion, and observations at 10 gigahertz, it turns out to be that the emission is negligible. We couldn't detect it even with the best systems that we have now. So what is happening is that we're not detecting the photosphere of the stars. We're either detecting mechanisms that produce very large brightness temperatures. For example, mechanisms that produce zero synchrotron emission, which is very bright in the radio, and that will make this number grow orders of magnitude, or the object is large. These two factors will make the flux go bigger. And let's say that we keep constant the distance to Orion, and we keep constant the frequency of observation, and that's what we detect. We really detect, for example, in solar mass stars, we detect this magnetic activity that produces geosynchrotron emission. In massive stars, we detect the wind, an ionized wind. In the radio, the radio photosphere is much bigger than the photosphere of a star, and that's why we can detect stars in the radio. We're really not detecting the star, but something associated with the star. Well, well, as you know, the topic of planets has exploded in the last 30 years. And as part of these milestones, at a point somebody detected a free-floating planet, and they said, because as I told you, we were thinking in planets as something that was a secondary product of star formation, and as objects that will be rotating around the star. But no, there happened to be free-floating planets, and in 2023, Pearson and McCaughrean did a very deep study of Orion using the James Webb Space Telescope in Orion. They used 11 filters from 1.15 to 4.4 microns. Of course, it is important to remember that this is not a spectroscopy, this is like photometry, and that will lead to some problems. That is, they are not seeing the detailed spectrum, but they are seeing like little bands, you know, like the bands that people have used in the optical, but somewhat narrow. Well, so this study made with the ultra-sensitive James Webb telescope, they detected more than 3,000 sources. Now, of those sources, 500 were objects of planetary mass, according to their analysis, that were distributed in Orion. But even more interesting, they detected 40 what appeared to be binary systems, 40 Jupiter mass binary systems, and then somebody came with the acronym JUMBOS, Jupiter mass binary objects. And here is an image of the James Webb. And we can see this, you see this, like here is the binary, and here is another binary. So well, they detected, as I said, some 40 of these objects. According to their analysis, which is made in the basis of this photometry, they concluded that these objects had masses between 0.6 Jupiter masses and 14 Jupiter masses. That is, they are, well, let's say below the threshold for planets. And then they are separated between the closest one is 28 astronomical units, and the most separated is 384 astronomical units. Well, this even complicated more the issue of why we have free floating planets. How are they formed? Because this is an artistic image, which is not a scale. Because if you think about it, in these systems, the planets are so far that from one planet, you may see the other, but like a small point, because they are separated by dimensions of the size of our solar system. But, well, this is just an artistic image. And so what is the problem about forming this? In Spanish, I'm using planetas errantes. Well, as I told you, I'm using the G's mass idea. It indicates that the mass of a planet is not going to control from a planet. You need more mass, and what is going to come out of this is a star. Well, so the idea is that okay, you form a planetary system, and these planets get ejected somehow. I will show you some theoretical ideas later. And but if ejecting one of these planets is difficult, ejecting a binary system is very difficult, because how do you eject these systems that are binary, and they are very separated, and they are just very lightly gravitationally bound. That is, if you add a kilometer per second to one of the planets, the system will break. It's a very weakly bound system. Well, okay, once this came up, we knew that a lot of people had observed Orion very deeply using the Very Large Array. And so we got this data and recalibrated and all the story. And we look for sources in all these jumbles. And we found that one of them, the number 24, does have a counterpart rating. So what is the nature of these objects? This is interesting. They both have about the same mass, and apparently this mass is in the range of planets. They are relatively close, 28 AU in separation. So at that moment, we had 3 observations with the BLM, and we found that the flux density total was about 50 microjoules, and that the spectrum was flat. This is another thing that let me come back later. At that moment, we could estimate, we could search for proper motions, because in these theoretical models of ejection of free-floating planets, well, one would expect that the planets will be moving at some velocity with respect to the frame of rest of the planet. At that point, we got not a very good limit, 15 kilometers per second. We see that we have improved this. And the sources, in these 3 epochs that we had, there was no variability, no circular polarization. And as in the infrared, we could conclude that the radio emission comes from both components at about the same amount. And also is that even when these are very weak in the sky, their luminosity is very high. It's actually higher, not since we don't have too many examples of planets with radio emission. Actually, there's only another example. The radio luminosity was very high, was hundreds to thousands of times the luminosity expected for a brown dwarf. All this was adding to the mystery. We tried to see what it was detected with ALMA, Mr. Pasta is the expert, and he didn't find any detection. Yes, please.
What wavelengths or what frequencies did you?
We work basically, a lot of work now is done at 10 gigahertz, because there is a very sensitive 8 to 12 gigahertz bandwidth, but we also use the 6 gigahertz, 4 to 8 gigahertz. So we don't use high frequencies or very low frequencies, because there are problems. High frequencies we see that are very noisy, low frequencies you get a lot of contamination. So this is not like the vision where you use when you don't know what's happening.
And the spectrum is flat.
The spectrum is flat, yes. And yes.
And these are detected by JWST as well, these sources.
By which?
But JWST by James Webb.
Oh yes, of course. They were originally detected by the James Webb, yes.
And
yes.
The emission is what, like a black body or something?
Let me explain. Okay, here it is. Well, actually, it is, it is roughly a black body. That is something that peaks in the near infrared, and they have their models in which they take a planet, and it's a planet that could be hot because it's just formed, and they model that, and from that they get an estimate of the mass, especially. As we will see, one of the problems with this group that has opposed this other group is saying, what happens is that this is actually caused by stars, not planets, and there is a lot of obscuration. So this obscuration will take away the blue part and will make everything weaker and redder. And so there is this debate now that will come. And apparently the way to solve this is to do a spectroscopy, because then there are lines specific to planets, like that will not appear in stars. Yes.
Do we have an estimate of their ages?
Of the ages
of the planets?
Yes. No, I don't know. I will have to check the Pearson. Yeah, that's a good point. That's a good point, because.
What if the star that they were, let's say, orbiting, when parent stability or some even produced a black hole which you cannot detect, let's say.
Right.
It depends on the age.
This is one of the models is to produce these rogue planets, is that the star actually becomes a black hole without ejecting, because we don't see anything, or it becomes a supernova, which we know is not the case. And that will actually create a rogue planet. So this is considered. Now, in Orion, we know that there hasn't been supernovas up to now, but something like you say, if you.
Well, it happened a long time ago, and that it'll depend on the age of the planet. So how you can.
Okay, yeah, well, a supernova could be the case. But the problem is that there are so many in Orion. There are so many in Orion that people think that they were formed in Orion. And there's a lot of theoretical discussion. Okay, so so here is an overlay. This gray scale is the James Webb image, and the contours are the VLA emission. And we ask for more time, ALMA time, and this high sensitivity array to see if it's a very compact object. And in here we're showing the 6 gigahertz image. And a referee had a very good point. He thought, well, there are 4 of these objects in Orion. So when you do the probabilities of an overlay, you have to consider all 4. What is the possibility that 4 objects coincide with the background source? And the issue is pretty small. It's like 10 to the minus 4. So the idea is that they overlap. Yes.
But you said that the emission was coming from both jumbos.
Yes.
Well, from both components. How can you know from the image radius?
Well, we have a somewhat better image at 10 gigahertz, and we see that the size of the radio emission coincides with, if you take the James Webb image and you convolve it, you get it like an ellipse because of the two orbits. So these two things coincide. And so the idea is that we're seeing radio emission from equal amounts from each of the planets.
Sorry, so this James Webb image has been composed to the VLA PSA or?
No, because one of the things with this system is that it is the closest one.
Oh.
But they have, I don't remember what frequency was.
But the James Webb, you showed some images that you could resolve both.
Right, those are the separated.
So in this one, you cannot resolve it, but they estimated two because of photometry analysis.
No, why would you say there were two?
Yes.
Well, we decided there are two because we try to fit the object with one source and it doesn't work. The source is like an ellipse. So the idea is that you have two objects there. And probably they see them, I think that they see them separated at the highest, the lowest wavelength of the James Webb. I think they do see them separated.
But this image is the VLA image, right?
The contours are the VLA image, yes.
And the color scale is the James.
Right, it's the James Webb.
Yeah,
The blue. Okay, no, this ellipse is what we get when we fit the James Webb data. So you get an ellipse, which suggests that it is two objects. But I think that at some microns, they do see both the separation. Now, this object is strange because it's the most massive of all. And it's also, I think it's the second closest. So, what all this means, we don't know. So, just a few months ago, we did new observations with the DRA. And now we have 5 epochs where we can get the position of the source. And we can try to see if there are proper motions. And so in these are the graphs how we present possible proper motions. This is the year, and we have data from 2012 to 2025. And this is the right ascension. And here again the year and the declination. And when we fit this, we don't get a significant signal. There's no, we only get an upper limit to the proper motions. When it comes out to these 6 kilometers per second, much better than the one we got when we only have 3 data points. So this is interesting because this certainly rules out a violent ejection mechanism that will make these things move at 10 or 20 kilometers per second. So that's it goes against formation mechanism that will involve violent explosions. But the problem is that people have come with ways of forming jumbos that are not moving with respect to the cloud. So this cartoon tells us how can we create rogue planets. And there are things that, for example, that you have a planet or a star, and some object goes across, and so manages to free this other planet. Here is the idea that they can form independently. Maybe there is some mechanism going on that allows small amounts of gas to contract and form a planet. That is with masses much more smaller than the James masses. The other possibility is that 2 stars sort of meet, and that could make one of the planets be released. And the other is related to what you were saying. A supernova explosion will be a way of releasing a planet. And probably some of the rogue planets that are seen in space come from something like this. Okay, well, now so people have discussed several mechanisms to form even binary systems. Now, as I told you, one of the things is Luckman last year has proposed that these are not binary planets, but they're actually binary stars. And the reason is why Pearson got confused. Well, because these are heavily obscured, and if you do photometry, you can confuse them with the planets.
But
Now, yes,
I'm sorry, but then they will be detected with ALMA, no? Because
there was
if they are heavily obscure, and then there's a lot of those concentrated around them, then they would be a detection in ALMA. But it's a non-detection with ALMA. So,
well, it's not really clear. That's a good point. You're saying if, you probably think that if these two stars were surrounded by a lot of dust, but I think they are talking of the two stars and that there is a
like a
screen.
screen.
So they get sort of avoid that problem. But all those things are possible. And actually, we got the ALMA time and we observe it in a few months and see we detect them. So, but Luhmann is, again, it's very, very interesting. This is the original paper of Pearson McCaughrean that were submitted in 2023 is not accepted. And actually, the referee of our paper said, your paper should not be accepted because you're talking of things that are in a paper that is not accepted. And we have to argue, well, what we do? I mean, it's always there, we already there. So the final paper was finally accepted. Okay, well, how do you form binary jumbos, binary methodology? Well, one possibility is this, and theoreticians have to explore this, is that you have the contraction of a cloud that's going to form a binary star system. But this system is like in Orion, or in the region that there are a lot of all these stars. And then the ionizing radiation is going to start photo-evaporating this cloud. In a way, as what happens with prophets and with other things that are in Orion that are being photo-evaporated by the radiation. And there is a group that is saying, if this works in such and such a way, this system that originally was going to form two stars ends forming two planets. Okay, well, that's one possibility. Another possibility that a group of Chinese astronomers has proposed is that you have a binary system of protoplanetary disks. And somehow this interact, I think this is done numerically, and there are planets in this, and this interact, and somehow these two planets are released as a binary system. I haven't really read the paper in detail. Well, now, let me tell you about radioluminosities. We don't really integrate over all the radio spectrum, but somehow we get an emission at a frequency and we correct for that, and we get some sort of a token for radioluminosities. And here is a compilation done by Caro and Pineda of the radioluminosity, which is here, of brown dwarfs. And actually, brown dwarfs come in single and in binary things. And we can see here that the binaries are, I don't know, maybe 2 or 3 times more luminous than the isolated single brown dwarf. We're talking here of brown dwarfs. And so we say, where does a jumbo 24 fall? Well, it falls too high in this graph. It falls in here. More like what you would expect from a binary stellar system. So in a way, our results also maybe favor what Luhmann is saying. For example, there is another object with apparently planetary mass that has been detected in the radio by Kao, and that falls below this, let me show you, it falls in here, which sounds reasonable, because we're saying that planets should be less luminous than brown dwarfs, and brown dwarfs less luminous than stars. So this object also, this SIM 0136, again is cataloged in such a way that it could be more massive, and it could be not a planet, but some sort of dwarf. But the jumbo is very luminous, even when in the sky it's ridiculously weak. What happens is that it's very far. Orion is far when you consider most of the work in exoplanets and in brown dwarfs is done very close to the sun. So the fact that we detected something so far means it is quite luminous. And so we go back to the question of what is the emission mechanism. Well, for example, we know that in our solar system, Jupiter has a magnetic field, and the magnetic field traps particles from the solar wind and creates this image. You see, the thing is that this is Jupiter, and I think the magnetic field will come like that. So the particles are trapped in here, and you get these points in here that emit synchrotron radiation. Now, synchrotron radiation has its characteristics. And for example, this will also work by Cow and Clean. It's very interesting. This is a brown dwarf. And they detected the brown dwarf. They actually, using very long baseline interferometry, they actually detected something similar to what is seen in Jupiter. There is two regions of emission that could actually be these two lobes that Jupiter has. But in the case of Jumbo 24, these do not appear to be the mechanism. So let me finish telling you a few more things about the radio emission.
A quick question about the previous slide. So in Jupiter, you say it's the solar wind particles that are captured by the magnetosphere. How are the relativistic particles produced in the ground?
That's a good question, because in principle, the wind is only 300 kilometers per second, but apparently within the wind, there are like turbulent motions that are very relativistic. And so it's not like the wind, but it's this local turbulent motions. Because in the sun, we do see geosynchrotron, which implies the presence of mildly relativistic
It's the same in the brown dwarfs. They have their own wind.
They're going with the wind. Yeah. The wind carries this relativistic particle. While the bulk velocity of the wind is small, there are these relativistic particles inside, or at least mildly relativistic. Although mildly relativistic do not explain synchrotron. So somehow there are also relativistic particles, which are sort of come with the wind, or the velocity of the wind is slow. Well, relatively slow. So let me finish telling you a few more things. With the help of Gisela and Laurent, we did very long baseline observations with something that is called the high sensitivity array. And this is a really powerful instrument that combines the VLDA, these 10 radio telescopes in the US and Hawaii and the Virgin Islands. Then it uses also the VLA and also uses the Green Band telescope, all together at 5.6 gigahertz. And what the result is that we do not detect sources at the level of 20 microjanskis. And it isn't clear, this is sort of like the level that we have 25 microjanskis for the sources, so we have to do more sensitive observations to be able to rule out that the emission is not coming or is coming from a very compact object, and that will limit very much the mechanisms for the radio emission. So let me then give you a summary of the radio data. One thing is that these 5 or 6 epochs we have observed the source in the 6 to 10 gigahertz region. The fluxes are constant. This is interesting because, for example, stars that have geosynchrotron radiation are very barren because this is related to magnetic activity in the star. This is pretty constant. Now we know that the emission is coming from both planets or both whatever they are. Another thing is that the index is flat. And we don't see circular polarization. The detection of circular polarization is a very good tracer of geosynchrotron emission. But the problem is if you do not detect circular polarization, that doesn't mean that it is not circular, it is not circular. But we don't see circular polarization. And this is also interesting. You don't need a very high brightness temperature. If the sources are, let's say, a tenth of an arcsecond in diameter, then you use the temperature of 100 Kelvin. So from all this, the people that do start with star formation, you say, well, this is consistent like with optical activity free to some extent. You know, the flatter spectrum, the lack of variability, the lack of circular polarization, the brightness temperature, which is not enormously big. And but we have a hard time trying to think how could this happen. For example, if we were to say that these two objects have a ring, an ionized ring, the spectral index should perhaps be more positive, and we're sort of trying to understand these things. Yes.
But a restriction on the side, non-detection by the VLBI of the object you did detect with the VLA.
Yes.
Then you say what its minimum size is.
What we can say is that it is, the problem is not just in the threshold, but in principle, in sensitivity, we could say it is bigger than, let's say, a milliarsecond. But
you can't there's a number on it at the moment.
No, what I'm doing here is that we know that it doesn't appear to be very compact. And from the upper limits to the size, we know that it is smaller than a tenth of an arcsecond. So from that, I get this temperature, which is not very much. I mean, it could be provided.
The separation of the two objects was about a tenth of an arcsecond.
Yes, about yes.
The externally photo-operated discs or externally photo-operated discs?
Well, that's a possibility because the properties in Orion have flat spectral indices because the gas that is photo-operated is not very thick.
Well, I suggested that the last time you gave it to a company, so I didn't want to repeat myself.
Or an externally photo-operated circumplanetary disc.
Well, that's harder because it will be bigger than the separation of the binary system, and that doesn't seem to be the case. Yeah.
For the radio emission, have you considered the cosmic ray flux? Cosmic ray particles. You can have a flux of charged particles coming in for cosmic ray electrons. I don't know how much is needed to produce such an emission.
How much is it to produce the radio emission?
Yes.
I could give you, I haven't done it, but I could, if you assume it is an emission, I can give you densities and everything.
It's an alternative to if you don't have winds from these boron dwarfs that are, you mentioned for Jupiter case, there's a sun that is giving out charged particles. You can have cosmic rays from other sources, supernovae or whatever, that could come there if there is no star. That's an alternative. Depends on how much flux you expect there.
Right. I haven't considered that because the emission we see from Jupiter is non-thermal and it has this very steep negative index. While in here we see a flat spectrum. But those are very good suggestions. Yes. And the last thing is that we don't see large proper motions, which would appear to go against some sort of violent ejection mechanism. But I mean, a violent ejection mechanism is probably ruled out by the fact that these binary systems will sort of break. Or maybe they are breaking. That's another thing that I was thinking. Maybe they are ejected from some sort of system, one of the many solar systems forming in Orion, and they are actually separating. But there are no good proper motions that could measure the separation, and the best we have is this proper motion of the binary system, which puts a limit for, it is not very fast velocities.
One problem with it being a growth, I think it's at 6 gigahertz, all the growth are optically thick. Right? Free, yeah? It's, or at least the bright ones are. I guess this is a lot fainter, so the emission measure could be a much lower, so the depth could be lower. And it could be optically filmed.
Right, because it's so weak. Yeah. If you this will be probably, I don't remember very well, but 10 to 100 times weaker than the droplets in the rain.
I think it probably could, because they have the bright protons have an optical depth at 2 centimeters of all the units. So this would be a much lower.
Yeah,
It was weak. It was a thing.
yes, all this, one has to explore all these possibilities. The topic is very interesting. We're all hoping for this James Webb spectroscopy that I don't know if it can be done. The sources are very good, but I think it can be done. And people is trying to do it to be able to say, well, no, they are really planets, or no, we did a mistake. They are long mass stars. So thank you very much.
Okay, we have lots of time for questions.
So in the original detection in the infrared, there is a population of objects, right? And it's only one of them that emits in the radio.
Right.
And what's so special about this object in the infrared? Is it like the brightest in the infrared, or does it have anything special?
It is one of the brightest. It is certainly the most massive, by the way. Both are in the threshold between planet and brown dwarf. And they are also very close. I think they are the second closest object. So they are especially in that sense.
Did you plot the properties of this object on this famous correlation of the centimeter luminosity versus the volumetric luminosity for thermal radio jets? Did you try it?
Well, no, that's a good point. That's a good point. Yes. It could be jets if they were optically thin. It's the problem that normal jets are partially thick at these frequencies, but these are so weak that they could be optically thin, these jets, and it would be like optically thin free. But that's a good point. I haven't done those. Thank you.
Are there any optical images of Orion, like made with adaptive optics, that could detect these things?
That's a good point. I think it would be hard in the optical, because since they were classified as planets, that means that they are probably peaking at a few microns or growing at a few microns. So I don't remember.
If it was optically thin free, then you can work out what the H alpha
should be right now.
Compare that with observation.
With the H alpha images, yes, that's a good point. Yeah, but that's a good point. I think they detected them. Although 5,000 objects detected, probably 3,000 or 4,000 were detected already in the optical. The regular stars are detected. Yes.
There's one on Zoom.
Yeah, Gilberto, go ahead.
Thank you, Luis. How do we know that these things are gravitationally bounded? What I'm thinking is, if they are ejected from the same place, they might be moving in roughly the same direction. That you couldn't be too far apart. So how do we know they are gravitationally bounded?
Well, that's a good question. We will need to do observations over many years and see that they don't separate more, but they could be separating. They could be somehow a system that was ejected from a planetary system, the binary was ejected, and it's just moving apart. And they are very lightly bound gravitationally. They would just separate and become individual free-floating planets. So we don't know. We don't know if they are bound. That's true.
The proper motions you presented were for the system, for the pair. So do you have proper motions for the individual components?
No, we don't have proper motion for the system as a whole. I guess that in the other systems, new images of the James Webb could reveal if they are separating. That is, if they actually not gravitationally bound, that they just probably were originated from the same place and they are just going apart. As I told you, the difference of 1 kilometer per second will make them gravitationally free. So they are probably breaking away.
Thank you.
But nobody has measured that.
Thank you.
Okay, so since we know the masses of the, do we know the masses of these objects?
Yes.
So for a brown dwarf, we could work out how it, what, you know, given the radioluminosity or in other bands, what their age has to be, just like we do for other stars.
Right. Let me check the Pearson paper if they talk about the age, because this is very important, because with age, both brown dwarfs and planets change a lot because they become cold. But I'll check it and I'll tell you.
Okay, in that case, let's thank our speaker.